Well, good morning. Morning, everyone, and welcome to the ABL market briefing. And welcome everyone online as well. I've just got confirmation that you can hear me on YouTube. So my name is Paul Hill. I'm the Global Technical Director. Some of you will know me. There's a lot of new faces here today, so welcome. New technology. What, up the other way? Yeah, no, it's not working. It's lost the plot. The whole thing's lost the plot. All right, thank you. Right, that should be the last technical hitch. So our briefing this morning is accredited by the Chartered Insurance Institute, and delegates can claim up to 1 CPD hour for participation. We will therefore keep a record of those of you in the room today and those of you logging online. If you haven't done so already, please make sure you sign in with the team on the desk outside after the briefing in order to receive your follow-up email and your CPD accreditation. So let's look at today's presenters. They're in the front row in front of me here. Paloma Medina is a graduate of our engineering development program, and having worked in Singapore and Exeter previously, she is currently a senior naval architect in the MWS renewables team based here in London. And Charlotte is also a graduate of the program. She's worked in Norway, Aberdeen and Southampton, and is now a naval architect also in the NWS team, focusing on renewables. And lastly, Nick Jones will be presenting today's case reports. And Nick is a senior naval architect, so there's a clutch of naval architects today. I don't know what you call it, and there's more than two, but there's a bunch of them. So he specializes in moorings and cable installation. He's worked on projects such as the Viking Link, submarine power cable connecting the UK to Denmark, and has also worked on multiple offshore wind farm projects, such as Dulwyn 5. And so please note the usual caveats apply here, and the Chatham House rules apply. Please also remember that the information contained in today's presentation, any opinions or comments expressed are those of the presenters and not necessarily those of ABL. At the end of today's briefing, can we please ask everyone to take 3 minutes out of their time to complete the online survey. This is really critical for us for our CPD accreditation status and allows us to continue to offer you 1 CPD point per briefing. It also means we can actively look at how we can improve these briefings to match your requirements and needs. Please use the QR code on the screen or displayed outside the room to download the survey. Don't worry if you miss it, we'll also send this out to you in a follow-up email. Before I begin today, we ask you to give a few moments thought to seafaring men and women at sea today. Even though COVID-19 seems increasingly in the rear view mirror, we know that seafarers are still working often longer than they're meant to because of crew change issues. There's also, of course, a multitude of other factors going on in the world which impact adversely on the lives and conditions of seafarers. Many of our colleagues come from a seafaring background, so crew welfare is a cause that's very close to our heart. As such, we are a signatory to the Neptune Declaration, which has undoubtedly played a part in many improvements to the lives of seafarers today. So please take a moment to look at this and perhaps consider getting your own company to become a signatory. Now, over to our presenters.
Perfect. Thank you very much, Paul. So today we're going to talk about the emerging risks in offshore wind from an MWS perspective. So first of all, as our maritime market briefings are CPD accredited, we'll start by running through our learning objectives for today. So you will hopefully gain a deeper understanding of the MWS's role in offshore wind. you'll be able to identify the future trajectory and trends of the offshore wind market, understanding the differences between fixed and floating wind farms. You'll be able to identify the possible risks that will be expected from the new technologies and understand how they are potential causes for incidents and resulting capital equipment damages. And you'll gain insight into possible areas that will require improvement or alternative approaches to overcome potential delays. We will also recap these at the end of the presentation. So firstly, we will briefly cover the role of the MWS in offshore wind, as it's likely something that some of you may already be aware of. So to understand the role of the MWS, firstly, we need to understand the reason for their presence. So this comes from the construction all risks or CAR policy, which is something many of you are likely familiar with, but for those of you that aren't, it's a policy that provides cover to the insured party and their contractors against losses in a project, from the fabrication stages through to the load out, transportation and installation phases, due to the high levels of risk and expense at these stages of a project. This policy can also sometimes cover a warranty period following construction for defects. So in terms of the presence of the MWS, this CAR policy will often have a clause within it called the Marine Warranty Clause, which requires the insured to engage with the marine warranty surveyor, whose scope is then outlined by the insured party and the underwriter. So the marine warranty surveyor is an independent third party and is usually chosen from a list acceptable to the underwriter. In 2021, the Joint Natural Resources Committee, formerly the Joint Rig Committee, that represents the interests of insurers writing offshore energy risks in London, issued the first code of practice and scope of work for renewables projects, and this has recently been updated. So this helps to define the role of the marine warranty surveyor, the activities that should be reviewed, witness approved, and outlines the minimum requirements. It should be noted, however, that the MWS's scope can differ slightly between different projects, dependent on aspects such as the value of the assets. So in terms of the role of the MWS, marine warranty surveys are essential to ensure that marine operations are carried out safely in accordance with applicable regulations and industry standards, and with the appropriate level of risk mitigation measures in place. So this is important for high value or complex marine operations, such as the offshore construction projects and transportation of heavy cargo. In terms of the role and the activities carried out by the MWS, there are three main parts of ensuring the compliance and reducing risk. So this is the review of all the documentation regarding the operation. So this includes calculations, designs, procedures, and also risk assessments. The MWS also ensures that the vessels to be used are in good condition for the specific operations. So this is typically done by carrying out suitability surveys. And then finally, we witness the operations being carried out on site, ensuring that the contractors are following the procedures that they've created, such as lift plans and using the correct and certified equipment. When we go on site, we have checklists to ensure that all the necessary aspects are covered. And once we're satisfied, we can issue a certificate of approval prior to the operations commencing. We then stay and witness the operations to ensure that they're still in compliance with the approved documentation. One aspect, however, of offshore wind that differs from oil and gas projects is that in offshore wind, there are typically many repeat operations, such as the installation of the foundations, and these often use the same procedures, equipment, and methodology. Therefore, instead of attending and witnessing the installation of every single one of them, in accordance with the scope of work for repeat operations, it's only required to witness 20% of these. And then we can issue a repetitive COA that means operations can continue without any changes. It should be noted, though, that often it's not the first 20% of the operations that are witnessed, and they may be spread throughout the project. So, for example, we might go and witness some after a big crew change or closer to the end of the installations. So this slide shows how marine warranty fits into the life cycle of a project. The scope of the marine warranty typically runs through the build phase, operations and maintenance, and then the decommissioning. Decommissioning is something that's not up until this point played a major part in offshore wind projects. However, now some of the early offshore wind farms are reaching the end of their design lives, which are typically 20 to 25 years, and the industry is starting to put more consideration into decommissioning and will likely try and take lessons learned from oil and gas. As you can see here on the left, there's another aspect which the MWS may get involved in, which is called approval in principle. So this is mainly for projects which have innovative or novel methods or technologies that are going to be used. And this is to help ensure buy-in from an early stage and make sure that there's inclusion of all of the potential risks. So this presentation is going to outline some of the risks and emerging risks in fixed and floating offshore wind, which are based on our experience. And as a group, we've worked on over 330 offshore wind projects, not just from an MWS perspective, but also owner's engineering and analysis. So I'll now hand over to Paloma, who will talk about the future of offshore wind.
Right. Thank you, Charlotte. Okay. All right, so let's look at where the industry is heading towards. We can all agree that offshore wind is booming, and with the need for more clean energy, it looks like it's only going to continue to grow. So how can the industry make more energy? First of all, we can have bigger wind farms. We can put these wind farms in deeper seas. We can have floating wind, so we can actually put the wind farms in deeper seas. There are also alternative energy sources, such as wave, tidal, solar. Ocean thermal energy converters, OTEC, have become an attractive new method for islands who are looking to have sustainable energy methods. There's also the new concepts of having energy islands, such as the one that's being developed by in Denmark and Belgium. And all those methods are powered by new technology that is constantly under development. And of course, with great power comes great responsibility. So what safety standards are we developing, and how will they shape the industry? Oh, sorry, wrong way. Right, in this figure, it gives a good visual description of the growth of the wind turbines. It compares rotor size, hub height, and power rating. We can see that in 15 years, the wind turbines have increased from 2 megawatts to 14, and have grown from 80 meters to 220 meters of rotor diameter. So the future designs are only getting bigger. The increase in power rating and size of the turbine brings new challenges and risks in the design, the installation, the maintenance, and at some point even the decommissioning. In this next figure, you can see that the offshore wind farms that are being developed in Europe, and it compares the distance to shore and water depth. We see the trend is going towards further and deeper seas. So foundations is a key element of wind farms, and the designs can vary. Here we see the different types of foundations we currently have, which are monopiles, gravity-based, and different types of jackets. As the turbines increase in size, this requires different solutions, which is where placing wind turbines on floating foundations would be the next step for offshore wind, as they can be installed in a more restrictive seabed or further offshore where you can find stronger and more consistent winds. However, this technology is still in its early development. There are currently numerous designs and solutions. We can have here three of the main ones, which is semi-submersible, tension leg platforms, and spars. For example, Windfloat in Portugal is a semi-submersible 3-column floating foundation, and High Wind in Scotland is an example of a spar buoy floating submersible, which can be installed in water depths of up to 80 meters. So all aspects of the wind farms are increasing in size. This includes the jackets, the substations, requiring bigger vessels to cover their transport and installation. The substations are very similar to oil and gas projects, and as further offshore, their concept and uses varies. Some of these OSS are manned, and others only provide a minimum accommodation to support the offshore vessels. Now, these substations are now also called OCPs, offshore converter platforms, and these are used in the renewable and in the offshore renewables for HVDC conversion for energy output. ABL's largest OSS installed was 18,000 tons in Germany. And we have spoken about floating wind farms. So what about floating substations? So this is the Fukushima Kisuma floating offshore substation. And this was the first of its kind and was moored with 4 spread catenary chain lines. So the complexity of the offshore wind project is also increasing. And as the projects move further offshore and increase in size, the conventional WTG installation, which is normally done on a jackup, as you can see on the slide, oh, you can't see it, on the left side, these jackups are limited by the length of their legs. And so we will need new methods to install these turbines. And on the right, on the left here, you can see the vessel on DP installing a turbine. For cable lays, we see that near shore, we can use dredgers with a quadrant. But as you go deeper and you go offshore, we'll need cable lay vessels. Finally, novel technologies are constantly under research and development to try and overcome the new challenges posed. Some very exciting new concepts are being created, but how do these realistically fit within the offshore wind sector? So now let's have a little look at what risks we will see in the fixed wind farms. So we have agreed that the future is to have bigger turbines. One of the key risks of this is that we're going to have bigger equipment for an installation. This means bigger vessels and bigger cranes. Do we currently have all these available in the market, or are we going to need to start building purpose-built vessels for these installations? Can we actually refit current vessels? Also, the lifting tools will be increasing. We can see that Siemens have had, for example, the Georgia, the Janet, and they are now currently in the testing of their new bigger blade lifting tool, which is for their even bigger blades. Secondly, we have the risk of needing new technology and the procedures that have never been used before. So as we conquer new deeper seabeds, the conventional installation method of the jackup is not valid anymore. And so alternative methods are required. This is the example of the Arcadis Ost, which was the first floating installation of a turbine and that just happened in November last year. A method to identify and mitigate these new risks includes contractors testing the new equipment and carrying out mock-up trials, which can be done on-site or even as a simulation. As MWS, one of the ways that we can help mitigate these risks is through assessing the documentation and the procedures and attending the operations to assure that these procedures are followed and reduce the risk. Often for the first installation in series, we will ensure that the weather limits are lower and more stringent until competency for the installation is proven, and then the limits can be increased. In addition, a good communication with the MWS is important. MWS companies have a lot of experience and lessons learned from the past projects. As Charlotte mentioned before, ABL have worked in over 300 renewable energy projects. Always retaining a third-party independence, of course, the MWS can add value and increase the understanding of projects and advise on success and failures of past practices, as this is done in oil and gas currently. Right, another risk that we need to look at is the qualification and the experience of our contractors. Well, on the one side, we have the current contractor who's trying to keep up with the increasing work demand of the projects, and they grow their size rapidly with new and inexperienced technicians, and they don't always provide the necessary learning tools or time to develop properly. On the other hand, there are the new players who want to get involved in the industry, and they do this by lowering their prices during the bidding process. The clients and the contractors need to be aware and do due diligence when selecting the contractors to ensure they have sufficient knowledge and experience for the specific operation to not generate an additional risk. It is important to remember that this attractive low price might become expensive in the end, and focusing on quality is a good way to help de-risk the project. A risk to consider is interaction between the contractors as well. So wind turbine will have different contractors for the foundations, the cables, and the turbine components. So good communication between the main players is important to ensure that all the risks are understood correctly. And finally, another risk from the contractors is, again, the misunderstanding of the role of the MWS. The International Marine Contractors Association release from 2022 specifies that the contractors should be involved in the selection and basis of engagement of the MWS. This is because when they apply for a project with a lump sum, comments with the MWS have cost them some money. So they should be involved in the choice of who makes these comments. This kind of goes against the whole point of having a MWS to reduce the risk. Right, so we have discussed the installation of turbines further offshore in the deeper seas. So what other risk will this bring? First is the environmental risks, environmental limits. These will remain very similar as we move further offshore. However, you will encounter worse weather conditions, which can lead to smaller weather windows and consequently weather delays. In addition, these areas are typically higher energy seas, and they bring big risk when you're looking at installing a tower onto a monopile. And consideration from both client and the contractors need to be kept in mind. This communication between all parties is key to capture the installation risks and the interface between the components. In addition, due to the lack of vessel availability, many operations are taking place in the winter months, which again increases the risk of weather delays. And these are not just weather delays on the installation, but also on basic crew changes, such as helicopter and CTV changes. Another topic to look into is the risk where we have touched upon is the drive to reduce cost. For example, in fabrication, by selecting locations where cost is less to produce, or due to the lack of local facilities with the capacity to carry out the work, this can lead to longer transit times and again, more delays. There are tools to carry out voyage simulations and metocean analysis to help identify and mitigate these risks that are associated with transportation. The image here presents, can I point? No. Presents an example of a safe trans analysis, which highlights in red, so a transport that's going from Asia to Northern Europe, and it highlights in red where the weather criteria will not be met. So due to many projects running in series and the vessel availability, there is a knock-on effect as well on projects which delays, and this can push a project to be carried at a different time of what was originally planned. So it might go into September and October when it was initially planned to be done in June or July. Now, cables. So cables make about 40% of the insurance claims. However, they are around 80% of the cost. So a single export cable can cost up to £12.5 million to repair. And it means that it's the most expensive cost and for the insurers, and it creates the most worry. So what types of claims are we looking at? There are three main areas where cable failures take place. It can be a fault from the manufacturer or a design defect. It can be a fault during installation. This is where you can find damages as compromised MBR, tension, compression, or possibly physical damage from a dropped object or an anchor strike. The last one is the latent defects, which can be from manufacturing or installation, but the damage only shows up later in the life of the cable, so perhaps after 10 years of being installed. For a cable to be repaired, it needs approximately 32 days from when the damage takes place to when the cable is repaired, and this includes getting the procedures, finding a vessel, and actually carrying out the operation. But of course, some can take even longer and be more complex. Some cable manufacturers are going into framework agreements with cable repair companies to ensure that they are prepared in case this happens and reduce the time and cost of such operations. There are different framework agreements. For example, having an upfront engineering in place is one way. There's also somewhere they're having the vessel on standby ready for the cable repairs. This latter one is useful if you have similar design of cables and joints, which is why telecom companies use them, but maybe not the best for wind farms, although it's something that they should start thinking if they have the same cable. As wind farms go further offshore, you will also require to have HVDC cables, otherwise there's too much voltage drop. This requires the need of an OCP, the offshore converter platform, to convert between AC and DC from the turbine to onshore. Additional complexities on the cable as you have to be laying them as a bundle. With cables, there's always a trade-off between the strength, their weight, and their flexibility. So some cables require more armor to protect itself from the surrounding areas. However, this means that they're harder to install and carry out load-out operations and pullings, so because the cable's too stiff. Then on the other hand, if you have a weaker cable, you are exposed to your exterior damages. So clients and contractors need to study carefully the types of cables that they will require. One thing that is currently causing some issues is CPS failure, cable protection system failure. So therefore, we currently take a more detailed review of the stability and fatigue analysis for these CPS. And these issues can result in the array cables needing replacing and rock stabilization. Lastly, we will look at O&M. So we will see the same types of risks that we have covered in the previous slides, but there are some additional risks that the O&M will bring. So these operations are usually carried out in a much shorter time frame than the T&I and are more reactive in nature. The process of creating documentation and preparing for operations can be undertaken in a couple of weeks, and therefore it's important to ensure that no corners are cut in this process. Having a client rep to oversee operations offshore to ensure the proper processes are carried out is a good way to mitigate these risks. And now I will pass over to Charlotte.
Thank you very much, Paloma. And now I will talk about some of the risks in floating wind farms. So floating offshore wind is predominantly in the demonstration phase, with most projects still under development. There are a few operational floating wind farms, with the one Paloma mentioned off Scotland, there's Hywind Scotland, and also the Windfloat Atlantic off the Portugal coast. These demo sites are much smaller in scale than typical commercial operations, with the two mentioned having 5 and 3 turbines respectively. However, they are useful for increased understanding of floating wind operations and collecting data. So floating offshore wind obviously brings about new challenges compared to fixed offshore wind. Primarily, this is due to the increased distance from shore and the depth at the sites, meaning that the very nature of floating wind and having a moving platform, which obviously greatly increases the complexity of the operations. So one of the risks to projects will be the lack of suitable vessels and facilities. So this has a few different aspects. Firstly, tow to site. So for towing the wind turbines to site for installation, this will require anchor handling tugs with a very large bollard pull, possibly about 220 tons or more. However, there are only a limited number of vessels of this size, about 50 in the world. Therefore, more vessels will need to be built. Otherwise, this will limit the capacity for projects, as they are already used for other purposes. There are a number of requirements for ports to enable them to be used for floating wind. These requirements depend on the different methods for fabrication and load out of the foundations. However, a couple of the main requirements are deeper water to enable them to be suitable for load outs and integration of wind turbines, and also possibly wet storage. Another requirement will be having a suitable quayside bearing capacity and storage space for the components onshore. And one other important aspect will be their proximity to site. So as there are weather restrictions on the tow, ideally they'll be situated as close as possible to the site. However, there are currently a very limited number of suitable locations for ports, so it could necessitate longer tows to the site. As I've mentioned, as Paloma mentioned, the greater distance offshore means longer durations of tows, and this will require longer weather windows, as these tows will typically be weather restricted to prevent damage to the turbines. This has the potential to cause project delays, and it's likely that each of these will happen in series, so these delays could also be cumulative. This increases the risk of contractors rushing to ensure that they're able to deliver on time and budget and to move on to the next project, and could potentially cause corners to be cut. In terms of time and resources, there are also concerns about the supply chain for fabrication and the lack of suitable facilities. So as mentioned, floating offshore wind is still a relatively new concept to a rapidly growing industry, and there are many new players joining the industry and introducing new technologies and ideas. As it's still in such early stages, the spread of technology hasn't narrowed yet. There's different designs of foundations, methods for fabrication and installation. In addition to new technologies, this will lead to inexperienced system developers and contractors potentially underestimating the risks of WTGs and not understanding their limitations, having had no track record in the industry. So an acknowledgement of this is the increased complexity of operations is shown through the MWS scope I mentioned earlier, issued by the JNRC, which in comparison to fixed wind, where certificates are only required for the installation of the first 20% of foundations, for floating offshore wind, every unit is required to have a certificate of approval. So it'll be important to think about whether there's been consideration of the contracting mechanisms within the project. Have you considered the experience that the developers and contractors have in carrying out this sort of work? Has there been sufficient testing, risk assessments for the new technology or methodology that's being developed? So moving on, we will take a look at cables for floating offshore wind. So for these cables, one question is to ask, for these cables, how will it be done safely and successfully, ensuring that the cable integrity is not compromised? Has there been sufficient consideration of the design and the fatigue life? So for these floating offshore wind, it's typically dynamic cables that are used, which have increased complexities, increased length. They take learnings from offshore oil and gas projects. So in their installation, it's more complex due to the installation of buoyancy modules. One other major risk is that there's no specific design codes for dynamic cables currently. Instead, the requirements are based on those for similar structures which may not be representative. But it should be noted that data about failures and maintenance from demonstrator projects and early projects will likely be used in future to better understand the fatigue life of the cables, in addition to extensive onshore testing. So one other risk is increased handling of cables. So if the turbines are required to be towed to port, such as for maintenance, this could increase the number of times the cables need to be connected or disconnected. So we need to look at how much does this increase the risk? So to tackle this, there are many systems in development looking at different connection types and innovating designs to increase efficiency in operations and to reduce the risk if the cables do have to be connected. One example of this is plug and play connectors, such as used for the Windfloat Atlantic. Innovative solutions such as these may reduce some of the risks of cable handling. However, they'll need to be carefully tested and assessed to ensure they don't cause additional problems. We'll now look at the mooring systems. So these are similar in some concepts to oil and gas. However, unlike oil and gas projects in which they typically have one large structure with multiple lines, in floating offshore wind, there's likely to be large numbers moored, each with a minimum of 3 lines. So one major aspect is looking at optimization of the systems for cost while respecting the redundancy requirements. So due to the need for these cost-effective moorings for multiple turbines and the cost of anchors and chains, there is the potential of sharing anchors, such as for the Hywind Tampen project, or that shown above in a honeycomb solution, which is being explored by CMAR. Other considerations are the access requirements and spacing for the projects, which put a strong constraint on the footprints they can have. In terms of risks, we also have to look at failures and the potential consequences. So some learnings from the oil and gas is regarding the failures of mooring lines and chains. In floating offshore wind, there's obviously a lot more structures moored. So there's an increased risk of failure compared to something like an FPSO. And also we have to look at the fact that there's large motions of these floaters. Another difference is that these floating offshore wind turbines are unmanned. So things like routine maintenance are more challenging. This does, however, mean that there's a lower consequence factor due to the loss of moorings, in addition to there also being no hydrocarbons. However, due to the relative close proximity of multiple wind turbines and the possibility of having multiple foundations moored to one point, such as shown here, if that point did fail, then this could have effects on multiple units, depending on the configuration, which could obviously be quite an issue for the project. So we'll need to consider in this design, are there suitable redundancy in place? Has the configuration been specifically designed for the site and the conditions that might be experienced? And moving on to look at O&M. So this is something, as I've mentioned, where there's tow-to-site solutions and also in-place solutions. So as the floating offshore wind develops, the number of these technologies will reduce and experience will be gained by personnel. So in development of these solutions, the involvement of marine warranty and third parties at an early stage is good practice and ensures that the risks will be considered. This will also help in the approval process. So there are currently technologies such as shown here. So these are the ones for in-site maintenance. The main risk here is obviously floating to floating is very difficult. So people are looking at solutions that are installed on the turbines. So you can see on the right here, there's a crane that connects to the foundation, or on the left, this is a different solution where it's a self-hoisting crane developed by Liftra. So for the tow to port, obviously there are restrictions such as the weather is a big one of them, the port availability, which I've mentioned, the risk of the connecting and disconnecting. So these are the different risks that you have to weigh up depending on which solution. As mentioned, the weather plays a large part in the project risks. Although the weather limits may be similar to those for fixed wind, due to the location of wind farms further offshore, there's likely to be higher downtime due to the higher energy seas and increased wind for possible maintenance. Part of the consideration will also need to be into how projects are managed due to the possibility of operations being carried out in marginal weather otherwise, as people rush to try and get the job done. In addition, other aspects to be looked at are human factors, such as the training of personnel to tackle this lack of experience. So moving on, we will look at a couple of other aspects that could pose additional risks to offshore wind and should also be considered. So one of these is climate change and resilience. So obviously climate and weather play a really important role in the design of offshore structures. And they're an important consideration during the lifetime of structures, from the transport and installation stage all the way through to the decommissioning. There are obviously many potential impacts of climate change, not only the change in temperature that could cause the sea level to rise, but also the changing weather systems could result in changing wave heights and wind speeds. And given the reliability of offshore wind on these climate systems, it's something that should be considered. Typically, we use current and historical data as a baseline for future design. However, it doesn't take into account potential changes that might be seen in the next 20 to 30 years, considering the design life of new structures. So when looking at new designs of wind farms, it's something we should ask ourselves, are these designs suitable for the future? Have the potential changes in the environment been considered? And finally, we'll take a brief look at the risks in contracting for both prime contractors and MWS. Although there is a shift coming to more of a cost plus time and materials model, a lot of the upcoming projects already have lock-in lump sum contracts, which were signed some time ago, and therefore contractors will need to service these contracts, which may not finish for another 3 years. Due to rising costs of resources, there is a danger of contractors not being able to complete their scopes or trying to pay themselves out of contracts or taking legal action to seek additional funds and cutting corners to try and deliver to a budget, the latter of which is obviously the largest risk for the insurers. So that brings us to the end of our presentation. Are there any questions in the room or online? None online. Anyone in the room? Yeah. Perfect. And just to conclude, we'll take a recap of our learning objectives today. So hopefully you've gained a deeper understanding of the MWS's role in offshore wind. Hopefully you can now identify the future trajectory and trends of the offshore wind market and understand the difference between fixed and floating wind farms. Hopefully you can identify the possible risks will be expected from the new technologies and understand how they are potential causes for incidents and resulting capital equipment damages or losses, both in construction and operation of projects. And hopefully you've gained an insight into possible areas that will require improvement or alternative approaches to overcome potential delays and achieve an overall successful project. Thank you very much. And I will hand over to Nick for the case reports.
Hey everybody. I'd first like to thank Paloma and Charlotte for the MWS comment. Oh, Jesus. The purpose of this section is to brief, simply keep you updated on the more recent higher cost incidents that ABL has been involved in, and in doing so, show you and remind you of some of the sorts of incidents and casualties that happen in the shipping and maritime operations. In case you haven't attended the briefings before, you might be asked, what are these so-called case reports? Well, these are largely, but not exclusively, hull and machinery casualties with estimated repair costs of excess of $250,000. Usually excluding salvage costs. They cover only a subset of total of the ABL group caseload, which of course includes many of the other areas apart from hull and machinery, typically between 10 and 20% of ABL case numbers. These case reports are also a significant subset of our H&M work, although they cover about 10 to 20% of the hull and machinery cases we survey by number. They cover about 65 to 75% of the hull and machinery cases we survey by costs. Treat with caution though, estimated costs are often preliminary and subject to further investigations and or inspections. In presenting the case reports for last months of activity, it's not attributing blame. We just aim to convey what happened, so we are not giving a definite conclusions about what caused, as many of the cases are still fresh, and it wouldn't be appropriate to do so in many of the cases because the investigation is still underway anyway. As usual, let's start off with some statistics. We've been notified of 11 high-cost cases during July. A bit low for these statistics, but you probably don't mind that. The blue columns in this graph show the proportional distribution by casualty type: 5 machinery cases, 2 lesions, 1 thruster damage, 1 stern tube bearing problem, and 1 coating damage, and 1 crane collapse in the other category. As always, this is such a small sample set, so you're bound to have gaps in the distribution, as you can see here, and compare the distribution across the whole year. In this case, of the whole of 22, given in the grey columns. With so many gaps this month, it's hard to be entirely convinced that this month the distribution is consistent with last year's trends, but normally we do find even a month's worth of data lines up reasonably well with what's year on year a fairly consistent picture. Here we've added the distribution of some of the 11 cases to the total costs, with no dramatic spikes this month, although maybe a little one for the stern tube bearing case. Individual costs have ranged from the threshold of $250,000 to just over $1 million. The total estimated cost for these 11 cases is just over $5 million, and the average cost for July is just below the $500,000 mark, about half of the typical annual average background figure of 1 million that we have seen over the many years in face value terms. These higher cost cases, individual extreme losses of over 50 million are excluded. So let's see how this year's community totals are panning out. In terms of casualty proportions by number, you can see that they're much more, as you can see, they're much more categories are now populated, apart from the last 3 columns. But these are still 5 months left to go, and as well know, things can change very quickly. Anyway, there's nothing particularly unusual yet at the moment regarding the relative incidence of different casualty types. And here we've added in the proportions of the cumulative costs. Relative costs of machinery cases are still high compared to where the past is. As we said before, we would expect the red column to be only half to 2/3 of the height of the blue column. The peak of the tail shaft, the seal category, is that we have seen since February, where we have a catastrophic fracture and has grown a little bit with this month's expensive stern tube bearing case, and a smaller peak in the other category that came from the piracy case back in April, which is subsidizing the average process as the year goes on. The average cost of the year to date is a bit lower than expected, coming in only at $700,000 compared to the long-term observed face value of an average of $1 million. But as I said, there's still a lot long in the year to go. Anyway, let's move on to now to some of the July cases in more detail. We've seen 7 of them. If we have time to go through them all, bearing in mind that although we say that the July cases, the month of is generally referred to as first advice that comes from our surveyor, and in some cases, therefore, it actually be from earlier months. First up, we have a 14-year-old feeder container ship that was berthed alongside a South Asian port load container from one early morning. Stevedores came on board to operate the ship's 2 cargo cranes. Unfortunately, it wasn't too long before the mishap occurred on number 2 crane at the rear. I understand that while lowering number 2 crane jib lift to the container from the barge on the port side, the jib suddenly fell onto the container pedestal on the deck, resulting in damages to the jib, both to the hook and heel ends, to the jib's side rails and to the crane wires. The story that while the operator started lowering the jib below the horizontal, which is beyond the allowable limit and which should be prevented by a limit switch, lowering the jib below the horizontal serves no operational purpose and is dangerous. The maximum outreach is achieved while the jib is horizontal, so you don't get it much more by lowering it any further. And lowering the jib below horizontal will not only significantly magnify the tension in the luffing wires that support the jib, but will also reduce the number of turns in the luffing wire on the winch drum, therefore the friction not able to hold the tension. Anyway, the ship's crew claim that they noticed the stevedore operator lowering the jib below horizontal and attempted to alert him, but he did not respond. Let's take a look at the damage at the end of the jib. At the hook end, here we see the arm of the jib is impaled on the container locator guide. And here we see the same thing on the other side. And here we can see, if you look closely, the pivot or heel of the jib has been damaged too on the slewing ring. Damage is clear if you look up from below. Lots of associated damage too, the sheave blocks, deck rails, and so on. The luffing wires and the hoist were also damaged beyond use. And here we see the luffing of the wire drum with no windings left on the end of the clamping bolts, bent from the final overload. Now, while the ship's personnel may moan about the stevedore's actions, the situation was certainly not helped by their leaving of the bypass key from the luffing limit switch here in the slot in the crane control panel. This key should be safely locked away, arguably $400,000 worth of damage, of avoidable damage. Next up, we have a 16-year-old Suezmax tanker appeared on our list a couple of months ago, having been towed from the Mediterranean repair yard, suffering $1.8 million worth of catastrophic damage to her engine's main hull bearings and crankshaft journals. The manufacturer service engineers attended on board to carry out those repairs. The process was dismantling the engine, found another $400,000 worth of damage. Here we see the top part of the big low-speed main engine with the cylinder heads removed. To the side, we see the top exhaust gas receiver, which receives the exhaust gases from the cylinder and feeds to the exhaust of the turbocharger. Driven by the engine exhaust, the turbocharger compresses the inlet air to the engine. The compressed inlet air is cooled and stripped of its moisture and passes into the salvage air receiver, ready for to pass into the engine cylinders, where the pistons move to the lowest position and expose the scavenge ports for the cylinder liners, which these openings are lowered into the end of the liners. The pressurized air rushes into the cylinders and displaces the gases out of the combustion port into the exhaust gas receiver, where we see earlier, and so on. Anyway, getting back to the point, I understand this is where the service engineers may have spotted the additional damage, as they noticed that there were sharp abrasions on the inner surface of the scavenge ports, indicating that there may have been some sort of contaminant in the lube oil or fuel at some point. When the engine is dismantled, they found classic symptoms of the presence of cat files in the fuel, broken piston rings, and vertical scoring along the cylinder liners. Replicas were taken from all the liners. As a result, the catalytic files were indeed concernable on the surfaces. The cause of the presence of the cat fines entering the engine are still under investigation. The big related questions are, as always, first, whether the fuel supplied and used since the last cylinder inspection was within normal limits for the cat fine content, and second, whether the onboard purifiers were working properly and had been properly maintained throughout the period. Quite a lot of digging needs to be done. The next case is for the main engine problem. It's a bit unfortunate. These things gone right wouldn't have cost the past $200,000. A threshold ended up on our high cost list. She's an early feeder container ship and was on the passage in the Far East, where the crack discovered on one of the main engine cylinder liners. Owners and authorities noticed that when the ship had arrived at a destination, the containers were discharged and more containers were loaded as normal. They had spares on board to carry out the repair. They just needed to move to a quiet wharf to carry out the liner replacement. Here on the right, we see the main engine, and on the left, you can see two of the spare liners that they carry on board, secured to the side of the engine. Shouldn't be any problem with making the change. Take the cylinder head off, whip out the damaged liner, and put the spare one in. Here, behind, waiting for the spare, we see an old cracked liner now successfully removed and stowed. The crack had been developed between two of the upper quill holes. These holes are into where the lube oil and supply nozzles or quills are inserted. These quills feed the cylinder liner surface with lubrication at strategic moments during the piston's travel up and down within the liner. Here we see the spare liner is now inserted into the engine casing, but there's a little problem. The quill holes in the liner do not line up with the quill holes in the casing. The spare liner is the wrong one for this type of engine. They checked for the second liner. This is the wrong type too. This all meant that they had to order a new liner, air freight it, and get it to the engine room. In principle, getting it to the engine room wasn't a problem, but above the engine is a soft patch where they can access for bulky items to get in and out. Of course, this hadn't planned on having to use it. And they had stowed containers on top of it. Yes, the excess hatch below this lot. So they would need to discharge again to get the new liner in the engine room. So from the process, from taking 2 to 4 days, it's probably less than $100,000. A repair that ended up taking 25 days, involved air freight apart, crane assistance, 2 tug moves, cargo discharge, and reloading, along with a rather large bill of $600,000. The case of the original line. The case for cracking of the original liner is still underway. This is a 10-year-old 156,000 deadweight tanker, which was in dry dock for a second special survey, where it's discovered white metal fragments when dismantling the certain seals. Things didn't go entirely smoothly in the repair either. They had already detached and repaired all 4 controllable pitch propeller blades in order to replace the O-ring seals when they discovered white metal fragments. This meant that they had to take off the blades again, remove the rudder in order to be able to withdraw the tail shaft and look at the stern tube bearings. And this is what they found. The aft bearing bush had been heavily scored with metal worn out, peeling near the propeller end, and I understand the forward bearing is fine though. With overheating, fretting being evident, the manufacturers recommended a new bearing. With damage like this, lots of cracks have been made on the condition, alignment of the tail shaft and the engine with respect to the stern tube bearings. On one side, we can see that although the intermediate bearing had suffered some slight scoring, these marks could easily be removed by the smoothing. The tail shaft had to be brought to the workshop for inspections and measurements. While again some slight scoring of the journals can be seen, it was hoped that the polishing could sort this out. Indeed, the tail shaft had been passed the quality checks and deemed to be fit to reinstalled in the ship. Here we see the successful results of hand polishing of the stern tube bearing. The propeller blades and pitch actuation system were also checked too, and no significant damage found here either. So quite a lot of dismantling, checking, reassembling required, contributing to the overall cost, but no further major parts apart from this aft stern tube bearing. As to the cause of all this is still an investigation. One possibility being investigated was as a result of the fouling of the fishing lines. The ship's crew provided the photo showing that the propeller, when the vessel first arrived in the repair yard, it seems to show something colourful found in the rope guard. This seems strange though, as it wasn't investigated before the propeller blades were put back on for the first time, as you can see there. Finally, we have 3 cases involving corrosion on our list this month. The first is about $650,000. This is a luxury motor yacht that had been transported on a heavy lift ship, and it seems that hot iron filings from the ship's exhaust had landed all over a paintwork. Some of these had melted and then rusted. Difficult to see unless you look very closely, but a whole new paint job is required nonetheless. The second case, concerning an alleged illusion between a tug and a steel concrete dock in the Americas, was more interesting to look at. To understand that the dock owners were very upset that the name tug had made a dent in the piling system where the tugs and barges were supposed to safely tie up to. Our surveyors were not very sympathetic at all of the owner's claim, however. If you look closely at the structure, there is literally not much of it. The webs and vertical members had almost entirely been eaten away by corrosion, so offer next to no lateral resistance. I'm not sure if it had been established whether the tug in question was actually anywhere near this part of the dock, and even if it was, the old question, fortune or inevitability, were perhaps relevant here. And finally, the third corrosion-related case involves rusting, rather unusually, both of the engines of this small 12-year-old crew transfer vessel. The vessel had been operating in the Middle East, but had been idle for about 10 weeks. She had been wet towed from another location and reactivation back into service. Allegedly, during the reactivation process, they had discovered that both port and starboard main engines had seized. Dismantling the engines, they had discovered not only a lube oil failure problem, but rather than a corrosion infestation problem. Here's just a few pictures of the components that had rusted. Seawater was found in the engine sumps, standing water found above the pistons, and several other cylinders. As for how the water got in the engine is still under investigation. One possibility being examined was it may have entered through the exhaust outlets during the tow, which, as you can see, would have been very close to the waterline. If that was the case, it could be argued that the preparations for the tow were somewhat wanting. Anyway, this is all we have time for this month. Hope you have found the sample of some interest. Let me hand you back to Paul.
Well, thank you, Nick, and thank you, Paloma, and thank you, Charlotte. Let's flip onto the last slide. That's the end of this briefing. Thanks, everyone, again, for joining us, both in this room and online. Don't forget this QR code, and please scan it for the feedback form if you can. And our next market briefing will take place here on Thursday, the 14th of September at 9:30. Watch out on our website and social media for more details. And we look forward to seeing you there. Now, if there's any more questions, if you want to just ask Charlotte and Paloma at the end of this, it's probably the best way to stay behind. We'll stay behind for another 5 or 10 minutes. So there we go. Well, thank you very much.